Okay, so here we have another pretty nice problem that uses roots of unity and or roots of unity filter, and I really like this problem because the algebra manipulation that you have to be a bit more clever with it than the other problems that we had, because you're dealing with like in this problem 11th roots of unity, whereas in other problems you can just like plug things in directly like I, negative 1 and 1. This one you have to be a bit different about it. So the problem came up on the USMCA tournament. And the question says that you have Sarah, who has 5 rings, and each of those rings has 10 rungs. So I've drawn 2 rings here for simplicity. And so she wants to paint these rings for some reason. I don't know, she's bored. And it asks if she paints a certain amount of rungs on each ring, how many ways can she do it so that she has painted in total a multiple of 11 rungs. And the key is that she paints them in contiguous blocks. So what that means is that if she were to paint 3, she could like paint these 3 which are next to each other, but she couldn't paint like say 1, 2, and 3 because those aren't next to each other, so they don't form a contiguous block. So the phrasing here that it needs to be a multiple of 11 means that it's pretty likely that we can solve this using a roots of unity filter, and we can create a function f of x, or we want to create a function f of x, which is the sum of a sub n x to the n. And so when you think about what the range of this is, I think it's n equals 0 to 50 or something. But if you like, the reason that roots of unity filter is nice is that you don't really care about what the range of n is. You just have to create your function and then just plug in values and it works. And what the a sub n represents is the number of ways that she can paint n rungs in total out of all the 5 rings. So for example, maybe she paints like 2 rungs on the first ring, 2 rungs on the 3rd ring, and 3 rungs on the 5th ring, and so that'll contribute to a sub 7, and so that'll be 1 way to paint 7 rungs, and if you add up the total number of ways that she can paint 7 rungs, that'll be a sub 7. So after we have constructed our function f of x, our answer will just turn out to be equal to a0 plus a11 plus a22 and so on, because this is like the amount of ways that she can paint 0 rungs plus the amount of ways that she can paint 11 rungs plus 22 rungs and so on and so forth. And so we want to find an alternative expression for this f of x which does not look like a power series, and then use our roots of unity filter to be able to isolate these terms and get our answer. So in order to figure this out, what we can do is first focus on one ring and find a generating function for that, and then use that to find our f of x. So let's call our g of x the same thing, except now it'll be like b sub n x again, and this is specifically for one ring. So b sub 5 will be the amount of ways that on one ring she can paint 5 rungs. So remember that it said that she can only paint in contiguous blocks. So what that means is, let's see what the first couple terms of this is. So if she were to paint nothing, then obviously there's only one way to do that because there's only one way that you paint nothing. If she were to paint, say, 1 rung, then there's 10 of these rungs that you can choose. So that would mean that you have 10 x to the 1. If she were to paint 2 rungs, this is where the contiguous part is important, because once you pick what the first one is, then you just follow that around. So for example, you can pick this one to be your first one and then you paint these 2, or maybe you pick this one to be your first one and then you paint these 2. So you pick like the leftmost and then you just go around how many times you have it. So that would mean that she can paint 2 rungs in 10 ways. Similarly, she can paint 3 rungs in 10 ways. So that'll be like you start here and then you go 1, 2, 3, or you start here and you go 1, 2, 3. So it's determined by the first place you pick it, and there are 10 of those places. And this keeps on going up to x to the 9th. So even at x to the 9th, if you pick here, then you just go all the way around to here. But then x to the 10th, so how many ways can she paint 10 rungs? There's only one way she can do that. That's because she paints everything. So no matter where she starts off, she's going to paint everything, so it's going to be the same thing regardless. So if they weren't contiguous, then these would be like binomial coefficients, and then you can find g of x in terms of some binomial expansion like 1 plus x to the 10. But anyways, how do we use g of x to get back to f of x? So the answer is just that f of x equals g of x to the power 5 because there are 5 rings. And so why does that work? Let's look, for example, at like a sub 7 again. So let's say that she picks, for example, 2 rungs from the first ring, 0 rungs from the second ring, 3 rungs from the fourth ring, 1 rung from the 3 rungs from the third ring, 1 rung from the fourth ring. How much is that one? And 1 rung from the last one. So we said that there are 10 ways that you can paint, for example, 2 on the first one. Then there's only one way that you can paint 0 on the second one. There's 10 ways that you can paint 3 on the third one, so that's 1, 2, 3, 1, 2, 3, and so on. And again, 10 ways we can do it here, 10 ways we can do it here. And so this will come out to be like 10 to the power of 4. So if she chooses like 2 on the first ring, 0 on the second ring, 3 on the third ring, 1 on the fourth ring, 1 on the fifth ring, there's 10 to the fourth ways to paint that. And so this is one possibility that'll add up to a sub 7, and this corresponds to b sub 2 x squared, b sub 0 x to the 0, b sub 3 x cubed, b sub 1 x to the 1, and b sub 1 x to the 1. So this one comes from your first g of x, this one comes from your second g of x, this one comes from your third g of x, this one comes from your fourth g of x, this one comes from your fifth g of x. And so let's say you had another one like 3, 0, 4, 0, 0. Similarly, you will have b sub 3, b sub 0, b sub 4, b sub 0, and b sub 0. And those will come from each of your different g of x's. And this one, if you look at the exponents, it'll come out to like x to the 7. And this one also, if you were to do that, then you would have some coefficients that will also multiply to something times x to the 7. And if you add up all those, then you will end up with a sub 7, which is what we want. So now that we have that, we can explicitly write this out as 1 plus 10x plus all the way up to 10x to the 9th, and then x to the 10th to the power of 5. So here you might be tempted to say that this looks a lot like a geometric series, and you would be right. So if this first one and the last one were 10, then this would be like 10 times x to the 11th minus 1 over x minus 1. And that's just because it's like 10 times 1 plus x squared all the way up to x to the 10, and that would come out to this times 10. But then you also have to subtract off the remaining terms, which would be minus 9 minus 9x to the 10th. And the reason is that if you were to expand this would come up with a 10 in the beginning and a 10x to the 10 in the end. So if you subtract these off, then it'll get you back to here. And that will be to the power of 5. And the reason that this is nice is because you are summing over all the coefficients where you have a0, a11, a22. And so this x to the 11 minus 1 will allow us to really cancel out a bunch of stuff. So we said that our answer was going to be equal to this thing up here. And we know from our roots of unity filter expression, then that is equal to the sum over the 11th roots of unity, 1 over 11 of f of z. So we're averaging f of z over the 11th roots of unity. And so we can try putting this in here. So we notice that this is 1 over 11 times the sum over z to the 11 equals 1. So notice that if we look at this part, right, we have z to the 11 equals 1. Here we have x to the 11 equals 1. Here we're just switching x for z, so that doesn't matter. So that would mean that for all 11th roots of unity, this will be 0. So that means that we can just like isolate this part. So that'll be negative 9 minus 9, and I'll just say z to the 10 because we're using z. And then to the power of 5. So now, there's one caveat, which is that if x is equal to 1, then you end up with 0 on the top, but you also end up with 0 on the bottom. So if z is not equal to 1, and if z is any of the other roots of unity, then yes, this expression is indeed this expression. However, if z is equal to 1, then you have to be a bit careful, because this will be 0 over 0, which is undefined. So what you have to do for that case is look back to here and look at what this is. So this quantity over here, if you plug in x equals 1, is just 1 plus 10 plus 10 plus 10, 9 times, because you go from x to the 1 to x to the 9, and then plus 1 again at the end. So that'll mean that you have this sum plus 92 to the power of 5. And so that means we also have to alter what this sum is taken over. So this is taken over z is not equal to 1. So again, you're splitting the sum into z is equal to 1 and z is not equal to 1. So z is equal to 1, you can pretty easily check that that's 92 to the power of 5. And this one is, this expression is 0 because z is in 11th root of unity. And so you just have this thing left over. So what are some manipulations we can do here? First off, you can see that z to the power of 10 is just z inverse. And why is that? Because z to the power of 11 is equal to 1. So what that means is that if you take any 11th root of unity and raise it to the power of 10, that's the same thing as taking its inverse, because z to the, if you multiply the 2, then you get z to the 11th, which is 1. And so now we want to evaluate what this is. And we can even factor out the negative 9 if you want. So we can take this as being negative 9 to the 5th times z plus 1 to the 5th, and this is z inverse. So now another change that you can make is, this is unnecessary, but since we're summing over the 11th roots of unity and we're taking z inverse, you can think of that as sort of being like a e to the 2 pi I n over 11, where n equals 1, 2, all the way up to 10, right? But the thing is, since we're taking z inverse here, if you plug in n equals 1, then you're taking z inverse, which is the same thing as taking n equals 10. And if you take n equals, say, 3, then taking z inverse is the same thing as taking n equals 8. And replacing this z inverse by az. So what that means is, like, instead of going forward from 1 to 10, you can just go backwards from 10 to 1, and you would get the same exact numbers, but in reverse order. So you can replace z inverse with z. That wasn't necessary, but I just didn't want to write down negative signs a bunch. So what we have here is, now that this is 1 over 11 times negative 9 to the 5th times the sum from z 11th is equal to 1, except we exclude z equals 1, and we want to look at z plus 1 to the power of 5, and then we add on 92 to the power of 5. So now what will this z plus 1 to the power of 5 look like? That'll look something like 1 plus something times z squared plus something times z cubed plus stuff, and then z to the 5th. That could just write something as z to the 4th, but that doesn't matter. This should be z squared, not z. Okay. So 1 plus something times z squared plus something times z cubed. I know the coefficients aren't hard, they're binomial coefficients, but the point is that the coefficients don't matter. So if you notice, like, since we're taking the sum over all the roots of unity of, like, say, z, we know that that should be 0, because that's our whole basis of the roots of unity filter, right? That, like, if you take z to the power of something and you sum over all the roots of unity, that will be 0. However, the problem is that we're not adding 1 to this. So we're taking the sum over all roots of unity which aren't 1. And so the way we fix that is we can add 1 and then subtract 1. So what we do is we can rewrite this as 1 over 11. This marker is dying. This marker anybody? Yes. 1 over 11 times negative 9 to the 5th times the sum over the 11th roots of unity. And so we're taking 1 plus something times z plus something z squared and up to z to the 5th. And now since we're adding 1 here, we also have to subtract off what this would be at 1. So that'll be minus 1 plus 1. We just plug in 1 into here, so that'll be 1 plus 1 power 5. And then we're adding 92 to the power 5 because that's what we had earlier. And so what we have here is that, so we have this expression is z plus 1 to the power of 5, where we're now summing over all roots of unity. And then this expression is we are subtracting off z to the power of 5 when z equals 1, because we're adding that here and subtracting off the same thing. So this will just be minus 2 to the power of 5. So now, since we're summing over z to the power of 11 equals 1, each of these guys is going to be 0, because, like, each of these exponents is less than 1. And none of them are a multiple of 11 except for this one, which has an exponent of z to the 0. And so again, this is our whole basis on the roots of unity filter. So, like, if you're summing over all the roots of unity of something which is not a multiple of 11, the exponent, then that'll evaluate to 0. If you having something that is a multiple of the exponent, which here is 1, then it'll be 11 times whatever that is. So that's just because, like, each of these is a number, and then you're raising that to the power of 0, which is just 1. So you're summing 1 11 times, because there's 11 roots of unity, and so you end up with 11. Okay, so now we have negative 9 to the 5th times 11 minus 9 to the 5th times 2 to the 5th plus 92 to the 5th, all divided by 11. And now we can combine some things, and so we can cancel out this 11 with here, and we have negative 9 to the 5th. Here we have a 9 to the 5th times 2 to the 5th, and there should be a plus because here you have negative sign, so that should be a plus. So that'll be plus 18 to the fifth, and then plus 92 to the fifth. And then this last bit will be over 11 because you distribute that. So what we finally have is that our answer up here is equal to 18 to the fifth plus 92 to the fifth divided by 11 minus 9 to the power 5. And for a quick sanity check, we can check to make sure our answer isn't completely absurd by seeing that this actually does end up being an integer, because remember the whole point was that you're counting the number of ways you paint something, and that should be an integer, right? So we want to check to make sure that 18 to the fifth plus 92 to the fifth is a multiple of 11. And to do that quickly, we can just take everything mod 11. So 18 is 11 plus 7, so it'll be 7 mod 11. And 92 is 88 plus 4, so that'll be plus 4 to the power 5. And this is taking mod 11. Now, a modulo 11, 7 is the same thing as negative 4, because 7 plus 4 is 11. And so here we have negative 4 to an odd power plus 4 to an odd power. So that means that you can take the negative to the outside, and this is congruent to 0, again, mod 11. So that means that our numerator over here is indeed a multiple of 11, and so that means our final answer is an integer. And if you want, you can pull out a calculator and check what that actually evaluates out to. But yeah, that's our answer to the problem of how many ways can she paint these. So that she paints a total of a multiple of 11 rungs on 5 rings.